400,000-ton supertanker is maneuvering through the Singapore Strait right now. The rudder is capable of turning 70 degrees to either side. The captain knows it, the crew knows it, and the helmsman will never turn it past 35 degrees. That's not an accident. That's not overcaution. That's one of the most carefully engineered limits in naval architecture. And the reason behind it will change how you look at every ship you see in harbor for the rest of your life. Because the real answer has almost nothing to do with turning radius, and everything to do with what happens to water when you push a blade through it too hard. Before we dive in, please tell us where in the world you're watching from and press subscribe. Start with what you think you know. Most people assume a ship's rudder works like a car's steering wheel. Turn it harder, the ship turns tighter. Push the wheel further, the nose swings faster. Simple, linear, predictable. The helmsman rotates the wheel, the rudder blade swings behind the stern, and the vessel does what it is told. It is not simple, not even close. A rudder is not a lever pushing against stationary water. It is a hydrodynamic wing operating in a flow field moving at 15, 20, sometimes 25 knots relative to the hull. That flow is not calm. It is turbulent wake shed from the propeller, mixed with boundary layer separation from the hull itself, all converging on a blade roughly 8 meters tall and 6 meters wide on a typical container ship. The rudder does not redirect that flow by brute obstruction. It redirects it by generating lift. Picture how an aircraft wing works. Air accelerates over the curved upper surface, creating lower pressure above the wing than below. That pressure difference is lift. That is what keeps 300 people and their luggage off the ground. A rudder does the same thing, vertically, in water. The blade is angled into the oncoming flow. Water accelerates over the curved surface. Pressure drops on one side, rises on the other. That pressure differential generates a side force that swings the stern and turns the bow in the opposite direction. The angle between the rudder centerline and the oncoming flow is called the angle of attack. At small angles, 5 degrees, 10 degrees, the water flows smoothly over both surfaces of the blade. The lift-to-drag ratio is favorable. The vessel responds predictably. Increase the angle to 20 degrees, then 30 degrees, and the rudder is still operating efficiently. The flow remains attached, the turning radius decreases, everything behaves as expected. Then you approach 35 degrees. Here's where it gets strange. Picture a river moving steadily through open country. Wide, calm, controlled flow. Now picture that same river being forced to make a sharp bend around a rocky outcrop. The angle is too severe. The water cannot follow the curve. It separates from the inner bank. Turbulence forms. Eddies and vortices replace smooth laminar flow. The organized energy in the stream is converted into chaotic motion. A rudder blade at high angle of attack does the same thing. As the angle steepens past 35 degrees, the water flow can no longer follow the curved surface of the blade. The angle is too steep. The boundary layer detaches. What was smooth laminar flow over the rudder becomes violent, turbulent separation behind it. In naval architecture, this phenomenon is called burbling. The water does not slide cleanly past the rudder anymore. It tumbles, separates, and creates a massive wake of disordered flow directly behind the blade. When that happens, the lift force collapses. The high-pressure differential that was generating the turning moment disappears. The rudder is no longer steering the ship. It is fighting the water. And the drag, the parasitic resistance opposing forward motion, increases exponentially, not linearly, exponentially. At 35 degrees, the rudder generates useful lift and manageable drag. At 40 degrees, the lift has dropped by 40% while the drag has doubled. At 45 degrees, the rudder has become a sea anchor. This is called rudder stall. It is not a mechanical failure. It is a hydrodynamic failure. The blade is still intact. The steering gear is still functional. But the rudder has lost the ability to do what it was designed to do. Instead of steering, it is now just a flat plate creating massive resistance against the ship's forward momentum. The vessel slows dramatically. The turning radius actually increases, not decreases. And the helmsman, expecting the ship to swing harder to port or starboard, finds instead that the ship is wallowing, bleeding speed, and responding unpredictably. The tactical diameter, the distance a ship gains laterally before completing a 180-degree turn, is carefully calculated during sea trials for every vessel class. For a typical 300-meter container ship at 20 knots, the tactical diameter at 35 degrees rudder is 900 meters. Increase the rudder angle to 45 degrees, and you would expect the diameter to shrink significantly. It does not. In controlled tests, the improvement is less than 5%. Sometimes there is no improvement at all. The rudder stalls. The ship loses speed and steering authority. And the turn actually takes longer to complete. That is the invisible wall that every commercial vessel is operating just below on every harbor approach you have ever watched from a pier. So where does the structural limit come from? If rudder stall is the hydrodynamic ceiling, why does 35 degrees appear in mechanical design specifications, steering gear, load calculations, and classification society rules that govern the physical components bolted to the ship's hull? Because the water is not the only thing fighting back. Start with what is actually happening inside the steering flat, the compartment deep in the stern where the rudder stock penetrates the hull. The rudder is not floating freely in the water. It is mounted on a massive vertical shaft called the rudder stock, typically 600 millimeters in diameter on a large vessel made from forged steel. That stock passes through bearings in the hull and connects to hydraulic rams or electric actuators in the steering gear room. When the helmsman turns the wheel, those rams push or pull on the tiller arm attached to the top of the rudder stock, creating torque that rotates the entire rudder assembly. The torque required to hold a rudder at angle against a water flow is not constant. It increases with the square of the flow velocity and the cube of the rudder area. Double the speed and the torque quadruples. At 20 knots with a 5-degree rudder angle, a typical container ship steering gear is generating 2,500 kilonewton meters of torque. That is the rotational force required to overcome the water pressure trying to slam the rudder back to centerline. Now increase the angle to 40 degrees. The torque does not increase by 14%. It increases by over 60%, climbing toward 4,000 kilonewton meters. At 45 degrees, the torque exceeds 5,500 kilonewton meters. The steering gear rams, the hydraulic cylinders, the tiller arm, and the pintles, the massive hinge pins that support the rudder's weight and absorb side loads, are now operating beyond their certified design limits. The rams can deliver that force briefly. Then, the seals begin to leak. The pintles begin to deform under load. And the steering gear is no longer controlling the rudder. It is wrestling it. There is a second structural consequence that most people never consider. A rudder turning at 35 degrees generates a side force that tries to swing the stern. That force is transmitted through the rudder stock into the hull structure. The loads are enormous. On a 100,000-ton container ship at 20 knots, a 5-degree rudder generates 3,000 kilonewtons of side force. The hull structure, the stern post, the rudder horn if fitted, and the bearings supporting the rudder stock are all engineered to handle that load with safety margins built in. Push the angle to 45 degrees, and the side force does not increase proportionally. It increases exponentially as the drag component dominates. The structural load on the pintles climbs by over 30%. The bending moment on the rudder stock increases past the yield strength of the steel, and the hull plating around the rudder aperture begins experiencing stress concentrations that were never part of the original design load case. Here is the mid-voyage reality check that most passengers and even some mariners never see coming. The steering gear is not the constraint. Read that again. The hydraulic rams and electric motors driving a modern steering system are not the reason a ship's rudder stops at 35 degrees. A well-maintained steering gear on a large vessel can generate 6,000 kilonewton meters of torque or more. If you commanded that torque to push the rudder past 35 degrees, the system would comply briefly. Then, the pintles would be operating past their fatigue design limits. The rudder stock bearings would be experiencing contact stresses that accelerate wear by an order of magnitude.